Yes. So I'm here to present our results on variability of the global ionospheric maps against JSON observations. Our goal was to compare and analyze both text sources, and this kind of side project from our main research, that is modeling and prediction of the ionosphere. But during the creation of the dataset, we saw some interesting dependencies, and I would like to show you today what we have found. So, first of all, what data we used for our study. So, we chose the global ionospheric maps from centers called ESA, IGS, JPL, UPC, and Wuhan with 2-hour interval, and those are final products from the centers. We wanted to have a long-term analysis on the spatial, temporal, and spatial-temporal ground. So against this, we stated the JSON altimetry observations from 3 missions, JSON 1, JSON 2, and JSON 3. And as you can already see, there will be a problem with the spatial analysis, since the JSON don't have data over the land. But this will not affect further results. So going forward, I will say quickly how we pre-process the data. So we know that between every JSON mission, JSON 1, JSON 2, and JSON 2, JSON 3, there is a bias, and the bias also is between the versions of the data obtained. So unfortunately, the calibration period for the satellites is pretty short. It's only 8 months, around 8 months. So we were able to only use the average value, average bias for this period. But first we applied the filter, 30-second moving median for this period to remove noise, and also we removed outliers before calculating these biases. And we obtained biases between the given missions and the versions, as you can see on the slide. So that's not all. Then we needed to apply some correction for the plasma sphere, because because JSON data do not contain whole plasma sphere. We needed to use some external model to interpolate this data. So we used the IAAC 2016 for this purpose. And also, the 1-second data is too dense for our analysis, so we resampled to 5-minute data. As you can see, this is represented by green dots, but it's still pretty dense and noisy. So for temporal analysis, we choose to calculate the 30-day moving average and moving standard deviation. But also to compare these two sources, so the global ionospheric maps and JSON measurements, we needed to interpolate global ionospheric maps to position epoch of JSON. Additionally, what I forgot to say, because we are doing modeling of the ionosphere, we also leveled up the JSON missions to JSON 3. So we applied the biases to previous versions. And here we have our first results of temporal analysis. As we can see at first, the difference with JPL center is highest, it's reaching around 4.8 tech units, while the lowest differences, 30-day moving average differences, we obtained for Code, ESA, and Wuhan. And it's probably, and you can see that they have similar curves, so this probably because of the use of the spherical harmonics in their solution. What is interesting, that for the standard deviation, we have really a higher standard deviation and really pronounced solar cycle in the ESA JSON difference. But, and we can clearly see ascending and descending of the solar cycle. What else we see? That the lowest standard deviation we obtained for the IGS and UPC. Going further, we have spatial variability. So in this case, we are back to 5-minute data, and we applied 2x2 window, and we were moving this window by half a degree to calculate statistics inside of this window. So as we can see, the lowest the lowest averages we obtained for the southern hemisphere. What is kind of, we can predict this because we have really good data for the oceans, for the JSON, while for the northern hemisphere, this data is not as great since of the high density of the lands and not many points to filter out. Again, the highest averages we obtained for the intertropical area for every difference. Now going to standard deviation, we have really similar results. So for the intertropical area, we again obtain the highest values, but they are not as high as we could expect. But this time the lowest standard deviations are on the north hemisphere above Tropic of Cancer. So it is caused by the land density, and global ionospheric maps have better quality around the lands in this case. So going forward, we performed some spatial-temporal variability. So we wanted to see the distribution of our differences against local time and geomagnetic latitude and longitude. And we can see here the really clear solar cycle. But what is more interesting are the one-year oscillations appearing here on these two graphs. It is less pronounced against the geomagnetic longitude, but it can still see. So after seeing that, we went further. So to see to study these oscillations, we removed the nonlinear trend from our data by applying 6-degree polynomial. And then we perform spectral analysis based on the Lomb-Scarwell method. So as we can see, we have really pronounced annual, semi-annual peaks. And what is really interesting, we can see some other peaks, like 117 days, 59 days, 27 days. So we studied it further. And this is still for the differences, and this is temporal, so it was for 30-day moving averages and standard deviation. So we did the same thing, but for the spatial-temporal analysis, when we again put this against geomagnetic latitude, longitude, and presented it as heat maps. As we can see here, we have really pronounced oscillations around, like annual oscillation, semi-annual oscillation, less pronounced oscillations around 90 days, 59 days, and 27 days. And we can see some gaps, and this can be caused by lack of the information from lands. So going further, now instead of taking into account the whole globe, we thought to take just the region, one region. So we took the square 10 by 10 degrees around the point 0 north, 0 east, and we calculated the same did the same analysis. But this is really interesting for us because it's kind of surprising that we obtained for every source, not the difference, for every source we obtained the same oscillations with really close up, similar amplitude. So we kind of assumed that we put the hypothesis that maybe the interpolation was the wrong choice in this part, because by interpolating we could just mess up the oscillations in the global ionospheric maps. And this confirmed our worries. So after interpolating to the JSON position and epochs, we obtained the global ionospheric maps, obtained their oscillations, and now we can see that for global ionospheric maps we have pronounced oscillation for annual, semi-annual period, for 27 days, that is connected to the solar turn around its own axis, and small peak, but peak for 121 days. Also, for the JSON, we can really see pronounced oscillation around 117 days and 59 days. To study it more, we performed the same analysis, but for more points around the globe to see if this is not only regional, but the global. So we did it for the lot of the points around the globe, and we achieved the same the same result. So we have really pronounced 117 days for JSON, 182 days, so semi-annual and annual. So what is this 117 days oscillation? We found out that this oscillation is caused by, it's more like a draconic period of the JSON satellites, and it was seen in the DORIS measurements already. But we were not expecting to see this in the TEC measurements, to be fair. So yeah, this is our small discovery here. And we tried to see if any like solar activity or geometric activity can be also the cause of this oscillation. But what we only found is that we have pronounced oscillation for 27 days for these indices and for semi-annual peaks. But we didn't find anything else besides that. We see some really small peaks in AP and KP around 120 days, but we couldn't connect this clearly with the 117 day oscillation. More we would connect this with 121 oscillation of the global ionospheric maps. So, to quickly conclude my presentation, I hope it finds you well. We found some pronounced oscillation that were in our data when we're trying to compute some, we're trying to do some modeling. And I hope this information will be useful for you when you will try to model yourself. So, if you have, you want more details about this, you can find this in our article. So, thank you very much.